Okay. So, good evening, everyone. So, today we will be discussing about the some commodity organic chemicals. Those are derived from biomass sources. So, in this session, we will be mostly discussing on something which are generally we use a lot in the industrial applications, some chemicals which are biomass derived, and there are various applications in the industry level. So starting with today's session, you can see this is a preview that we have already gone through lot of processes to convert our biomass sources into various useful products like liquid products, liquid fuels, and or the commodity chemicals that we generally derive from the lignocellulosic biomass sources. And so this can be achieved by thermochemical or hydrolytic processes. You can see in the flowchart that sorry, lignocellulosic biomass, this can be gasified to get syngas, and from the syngas we can also get methyl alcohol, and from that we can get BTX or lower grade of olefins. Whereas lignocellulosic biomass feedstock, that is pre-treatment has been done to separate cellulose and lignocellulose, to separate cellulose and hemicellulose from the lignin, and that part is further hydrolyzed and fermented to form our ultimate commodity chemicals. Those are alcohol, diols, or acids. Other than that, when we go for lignocellulosic biomass feedstock to produce pyrolytic oil via pyrolysis process, from that oil we can also produce lower grade of olefins. So this is some primary conversion processes of lignocellulose, from where we get various kind of industrial organic chemicals as a from the lignocellulosic biomass sources. Now coming to the this right hand picture, you can see that we are also processing various kinds of oils and like plant oil or algal biomass oil and other fats and triglycerides. So we are mainly deriving triglycerides out of these fatty acids, and from that we get glycerol fatty acid ester. So from that we go for various kind of um, microbiological processes like fermentation, and we get carboxylic acid and also um, epiclohydrin, or you can say 1,2 propanediol, or you can say ethylene glycol. These kind of downstream uh, commodity chemicals we can produce out of this well known or previously described processes, right? We have last like this session, and next session will be the last session for this course. So we have already discussed all the processes in details, right? That how the gasification pyrolysis, or how the triglycerides are break down into glycerol or fatty acid esters, and then how is the fermentation process is going on. So we have already discussed the main conversion processes. Now in today's class we will be mostly focusing on the uh, downstream commodity chemicals. Those are hugely in like applied in the daily applications, like production of polymers or resins. These kind of huge applications are there, right? So When we talk about the conversion of biomass into commodity chemicals, there are two philosophies for the conversion of cellulosic biomass and the constituent other building blocks. One is we go for complete deoxidation, two dropping petroleum hydrocarbon and further processing to commodity chemicals by incorporating like those processes into existing petroleum industry, like industry reactors, right? Other we can go like direct conversion to oxygenates or nitrogenates as a platform chemicals. So many commodity chemicals are oxygenates that are produced in a traditional oil refinery from the petroleum hydrocarbon, which are followed by catalytic aerobic oxidation. So we do oxidation of those chemicals and make the oxygenates, and those oxygenates are mostly used as a platform chemicals for other platform chemicals or the building blocks for other production of the various chemicals, like. So, in contrast, the carbohydrate building blocks, those are already containing multiple oxygen uh, containing functionalities in the biomass sources. It would not be logical to first remove all the oxygens from the petroleum hydrocarbon and then reintroduced those oxygen functionalities by the oxidation, because we are dealing with the biomass sources, and those biomass sources are already like enriched with the oxygen, various kind of oxygen functionalities. So here we have the privilege to directly synthesize those oxygenates from the biomass, and we can directly use for the like platform chemicals for production of the various other chemicals. So it will not only promotes the minimization of changes in the oxidation state, but also it is also help us to reduce the energy consumption, like we are not going for the any catalytic oxidation process. We are directly getting the oxygenates and nitrogenates from the biomass sources conversion products, right? So uh, when we talk about the various strategies for conversion of hydrocarbons like carbohydrates like hexose and pentose, those are building blocks of cellulose and hemicellulose, uh, respectively, to the petroleum hydrocarbons we can convert, right? So one approach is to produce the lower alcohols like ethanol, propanol, butanol by fermentation, and to dehydrate them to the corresponding olefins, thereby providing a direct link to the existing petrochemical supply chain. So when what we are doing here, that C6 and C5 sugar blocks, mostly these two sugars we are handling for the conversion, right? So C5 and C6 sugars, we are going for the fermentation process, and we produce the carbohydrate to hydrocarbon, and this hydrocarbon can be isoprene, isobutene, butadiene, and other chemicals, right? And other, we can also get alcohol and diols. From that we can also get as a downstream process hydrocarbon like ethylene, propylene, butene, butadiene, xylene, this kind of thing. Other hydrocarbon we get kerosene, aromatics, and gasoline. So these are like very briefly it has been described in this flowchart, that how our carbohydrates, the main building block, can be converted through various biological processes as well as some chemical processes to get the hydrocarbons. Those are like very similar. Similar means those are directly the one we can get as an alternative of the petroleum sourced, and we can also use those bio-sourced hydrocarbon in the existing petrochemical supply chains, right? uh, one butanol, it is one of the chemical which is receiving lot of attention as a second generation biofuel with a higher energy density as well as lower volatility than ethanol. So metabolic pathway engineering, the advanced engineering, has been also used to develop the recombinant microorganism, different microorganism. Those are able to efficient the process to produce butanols in a commercially viable yield. So this one butanol or the butanol, which is and the another name, it is also a good commodity chemical produced from the biomass sourced. So bio-based 1-butanol or its isobutanol can readily be dehydrated to produce 1-butene and isobutene respectively. So the availability of such bioethylene and biobutene would provide a basis for the production of different biopropylene by olefin metathesis, thus completing the C2, C3, C4 triads that form the main blocks for the petrochemical industry. So this butanol and isobutanol and the corresponding butene and isobutene, so these are some good commodity chemicals. Those can be like hugely used in the petrochemical industry. So another C4 petrochemical building block is butadiene, which could be produced by dehydration of 1,4 or 2,3-butanediol, both of which are available from the fermentation, simple fermentation of C5 and C6 sugars. Also, we can do in an alternative way that butadiene and other commodity chemicals can also be produced from bioethanol. Thus, bioethanol is sourced from the various kind of biomass sources, right? So another approach is the chemi-catalytic conversion of the bio-derived oxygenates. Those are mostly like we are replacing the petroleum sourced with these bio-derived oxygenates such as glucose, sorbitol or glycerol by so-called the process of chemocatalytic conversion, that is aqueous phase reforming over the combination of solid acid and dehydrogenation catalysts such as palladium or platinum, which produce a mixture of hydrogen and various kind of light alkenes. So further processing by hydrotreatment of this dehydrocyclinization cyclization over the modified zeolite catalyst, it affords also the mixture of production of gasoline, diesel and kerosene ranges alkenes and their standard mixture of BTX. So-called BTX means benzene, toluene and xylene respectively. So though there are alternative production of hydroxymethyl furfural, which is known as HMF, the product of the acid catalyst hydrolysis of hexose. Hexose such as fructose and glucose can easily be further converted to other hydrocarbon fuels. So, when we talk about a biorefinery concept of aromatic hydrocarbon, those can be produced by upgrading different pyrolysis oil also via aqueous phase reforming of carbohydrate feedstock. Alternatively, the lignin, which is a potentially good source of aromatic molecules, those and the global production of the lignin is more enough to supply the global demand for various aromatic molecules, and from that those are sufficient enough to produce different kind of like butyric acid and different kind of acid which are the commodity chemical of biosourced feedstock. So you can see some of the example of in this flowchart that commodity chemicals which are produced by fermentation process of biomass derived sugar. So C5 and C6, that building block sugars, can be utilized to produce these many of different kind of commodity chemicals: adipic acid, succinic acid, 1,4-butanediol, 2,3-butanediol, 1,3-propanediol, acrylic acid. This is um, this is hydroxyproponic acid HPA, lactic acid, itaconic acid. So these are different kind of acids that we can produce as a commodity chemical. So that we are using, that we are saying that via biotechnological processes or chemical processes, we are getting all of this. Some example like a wide variety of the oxygenates, lower alcohols, diols, mono or dicarboxylic acid, those can be produced directly from the carbohydrates in a redox efficient manner by different fermentation process. Various short chain diols, such as which are examples of the commodity chemical with many industrial applications in the mostly polymer and special chemicals, which can be produced via fermentation process. 1,3-propanediol, for example, it is a product with a enormous industrial application, which is most well known for the production of polyester or various kind of polymer which are used for fiber and plastic and other coating formation. Similarly, 1,4-butanediol or 2,2,3-butanediol, so these also can be produced effectively by fermentation process, which has a variety of potential industrial application. The main application of 1,4-butanediol is in the production of the polyester, such as polybutylene and terephthalate. So this is one of the most important application of 1,4-BDO. So these are some examples of the commodity chemical and their application. So we will be discussing some of the applications and their properties in details in subsequent slides. So lactic acid, which is also a good example as a first generation bio-based commodity chemical with many applications, and very important its application is a rapidly growing polylactate from this lactic acid as a bioplastic. Citric acid, which is also an example of the commodity chemical, also is produced like in a good quantity by the well-known fermentation process. So there are other many examples of second generation carboxylic acid, which can be produced in a cost-effective manner by fermentation process. Those carboxylic acid like succinic acid, it is also gaining lot of attraction because of the potential large volume application in the polyester and polyamides industry. Bioacrylic acid is also available via fermentation process of 3-hydroxypropenic acid and subsequent dehydration. We get the acrylic acid. So in different chemical processes, acid catalyst hydrolysis of pentose and hexose, that is C5 and C6 sugars, affords furfural or hydroxymethyl furfurals, which are also having lot of potential as a platform chemicals. Means platform chemicals means from that chemicals a whole lot of other subsequent chemicals can be derived. So this HMF can be further converted into levulinic acid and like GVL, that is also uh, valeror acetone, or it can be like dicarboxylic acid of furan like 2,5 dicarboxylic acid. These are some potential building block for the polyester synthesis. So HMF or LA or GVL are of interest both as precursor for the hydrocarbon fuels and also as a different commodity chemicals. So conversion of hydrocarbon fuels involves combination of acid catalyst dehydration and catalytic hydrogenation, whereby hydrogen required can be produced by catalytic aqueous reforming process of the different carbohydrate feedstock wherever hydrogen is required. So this hydrogen formation from the biosourced we have discussed in one of the classes, right? So this hydrogen wherever it is required for this hydrogenation process for producing this commodity chemical, that hydrogen is itself produced by catalytic aqueous reforming process of the carbohydrate different feedstock. So similarly, the acid catalyst reaction of the HMF with ethanol affords this alcohol, ethoxymethyl furfural alcohol, which is also hydrogenated to give potential diesel fuel as an additive and from two renewable feedstock and hydrogen. Catalytic oxidation of glucose, it affords the formation of gluconic acid, which is further oxidized to glucaric acid, which is one of the top 12 building block chemical that can be produced from biomass or renewable raw material. It is, for example, that an interesting monomer for preparing biodegradable polymers with unique properties. So this catalytic oxidation of gluconic acid also plays a good role for various production of the biodegradable polyamides or as a with unique properties. Another potential interesting sugar derived platform chemical, that is isosorbide. So this is produced by hydrogenation of the sucrose to sorbitol, which is followed by acid catalysis dehydration method to sorbitan, and subsequently isosorbide is produced. So, in to make it simple or very brief about what are the chemical that we can form, uh, see, this is like sugar we get. It can be C5 or C6 sugars. It is taken for fermentation process, and we get different kind of alcohols like ethanol, acetic acid, either lactic acid. So from that we go for different chemical synthesis, and we get lot of example. I am writing some of the examples like acetaldehyde. We also get acetic acid, ethyl acetate, butanol, pyridine, glycol, butadiene, acetic anhydride, and lot other examples. So, moving to the next, sorry, yeah, moving to the next part of the discussion, we will focus on glucose, which is like fermented and give mostly lactic acid. Okay, okay, we will discuss the structure of these chemicals in the respective slides. Lactic acid, succinic acid, 3-hydroxypropanic acid, itaconic acid, and glutamic acid. These are some commodity chemicals we are mostly get, and there will be other chemicals derived from these building blocks. So coming to the first, lactic acid platform, lactic acid as a platform chemical. Lactic acid, which is also known as 2-hydroxypropanic acid, can be produced by chemical synthesis or fermentation process of different carbohydrate of like uh, glucose, maltose, sucrose, lactose, and there are other sources that you can see. So it is a very common industrial chemical known for various industrial applications in food, cosmetics, textile, pharmaceutical industries, and recently these had emerged into bioplastic industry for production of the polylactic acid, which is PLA. This lactic acid is commercially produced today mainly through different fermentation process of glucose. The production of lactic acid is around 3 lakhs tons of lactic acid per year, and the worldwide growth is believed to be increased 12 to 15% per year. So you can see how much demanding commodity chemical it is, this lactic acid. It is also listed as a potential building block for future use in the US Department of Energy report. It was mentioned, making it one of the most useful chemical that has received great deal of attention worldwide. So lactic acid exists in two optically active isomeric forms, which is L form and D form, like L lactic acid and D lactic acid. It is utilized in food, chemical, pharmaceutical processes, and cosmetic industries. Lactic acid is a bifunctional compound bearing a hydroxylic group and a acid function, being it is different numerous chemical conversion it can be done from the lactic acid to other useful products. An interesting application which is currently receiving great attention, that is, it is used as a monomer for the synthesis of biodegradable polymer, which is the polylactic acid, which is PLA polymer. It can be used as a good environment friendly alternative to plastic that are creating problem nowadays, and we can substitute the petrochemical material. The presence of the chiral carbon atom in the lactic acid structure, which is optically active, it supports the formation of a crystalline structure and good stability of the PLA. So this PLA, it also exhibits high heat deflection, good biodegradability in nature, and it is also environment friendly because it is biodegradable and high potential to replace conventional petrochemical plastic material. Presently, the worldwide market for the PLA is nearly 105 metric tons per year, which is being also predicted to be increased 28% in 2025 due to applications of PLA as a good substitute of the polyethylene terephthalate. So it is a good substitution for the petrochemical based plastic material plastic material synthesis. Okay, so we can see a quick flowchart for the lactic acid production platform. This fermentation product, that is calcium lactate, it is taken 10% by weight, which is mixed with the sulfuric acid fed in the fermented reactor, and then the it is fed in a reactor maintained at 30 degrees Celsius, and then the centrifuge and other drying and filtration is taken place to produce 68% concentrated lactic acid. So where is the problem? That the recovery of the calcium lactate from the fermentation broth is very difficult, and the in the conventional process for the recovery of the lactic acid is still far uh, like it is still not up to the mark of the ideal collection or ideal recovery. It cannot meet. So indeed it has some bottleneck of the process as a shortcoming, you can say. So indeed it involves the precipitation of the calcium lactate after the separation of the microorganism and conversion of the salt to the lactic acid by addition of the sulfuric acid in the process. So the dilute lactic acid then produced by submitted to the purification process, and separation and purification stage up to it takes 50% of the total production cost. So you can see how much costly it becomes when it comes to purification and separation. So, moreover, when we talk about the reactor productivities, it is very low, and the processes are not so much environment friendly because it consumes lot of sulfuric acid to produce large quantity of the calcium sulfate, and it we can see that 1 ton of calcium sulfate is produced per ton of lactic acid production. So there has been recent researches and advances has taken place, like we are applying membrane based separation and purification technologies, particularly micro and ultrafiltration process and electrodialysis processes, which has a low cost of production of this lactic acid, followed by uh, very minimized environmental problems compared to the this conventional process. So we are now introducing membrane-based separation and purification process instead of this falling film evaporator. We can see here that these many of various various chemical processes can be followed to produce various commodity chemicals out of that. So here we have seen, like, we can produce 1,2 propendiol or lactates or PLA, lactide, pyruvic acid, also acetaldehyde, acrylic acid. So these many of chemicals we can produce based upon this lactic acid as a building block. So coming to the first process, that is polymerization process of the lactic acid. So uh, we are getting product of PLA. Okay, so the process seems like the sugar compounds are fermented to produce lactic acid as a fermented product, which is followed by polycondensation process to produce the oligolactic acid, and then it is cyclization depolymerization reaction is happening to produce the lactide as an intermediate product, and from that the ring opening polymerization is followed to produce the high molecular weight PLA. So as a PLA, there we can see, like, there is growing demand for the biodegradable polymer that we can bring into market as a substitute of conventional plastic material. So this lactic acid polymer consists of mainly lactile units, which is having similarly D or L D or L forms, just like lactic acid. So this lactic acid doesn't polymerize directly to the large extent due to some competing depolymerization reaction in which the cyclic dimer of the lactic acid is generated. So this limits the high molecular weight PLA formation. So the current route for producing the PLA involves first oligomerization of the lactic acid, and then it is followed by depolymerization to produce dehydrated cyclic dimer, which is lactide, and then it is followed by ring opening polymerization to produce the high molecular weight PLA. The polymerization mechanism can be cationic, anionic, or coordinative, uh, or can be proceed with reaction of free radicals. It can be catalyzed by various transition metals like tin, aluminium, lead, zinc, and bismuth, and any other. This kind of transition metals can be used as a catalyst for this conventional process of um, carbohydrate to PLA production. Then it comes esterification process, which is mainly focused on the production of lactide. So we have discussed lactate is in this slide, that lactate, it forms in the intermediate product. So as an intermediate product, lactide is formed, but this lactide also have lot of applications in the industry itself. So lactate, which is chemically, it is known as 3,6-dimethyl 1,4-dioxone 2,5-dione. It is a cyclic ester which is coming as an intermediate product in the production of the PLA. The optical stereoisomer of the lactide is L-lactide, D-lactide, and mesolactide. You can see in this figure, which is like some are optically active, but this mesolactate is optically inactive. So this variety of the lactide, it play a crucial role in determining the physical, chemical, and mechanical properties of PLA. By self-esterification, there are two esterification process. One is self-esterification process. Another one is like it is being esterified with another alcohols. So there are two processes. So in the first, by self esterification process of lactic acid, it produces linear lactic acid, lactate, and also cyclic lactate. This lactate is a very important compound which is can be used as a monomer for the production of the polylactic acid, PLA, and also polylactide or other copolymers we can produce. Different heterogeneous catalysts are used for this preparation, just like zinc oxide, then stannous sulfate or octanate, and their mixtures can also be used as a catalyst for the synthesis of lactate. So the esters of the lactic acid and alcohol, like alcohol can be used methanol, ethanol, butanol. It can be like produce non-toxic and biodegradable high boiling liquids having very excellent solvent properties, and those can potentially replace the toxic and halogenated solvents for a wide range of the industrial uses. This lactate esters as an intermediate can be used as a plasticizer in the cellulose and vinyl resin, which enhances the detergent property of the various ionic surfactant. So these compounds are very useful in the preparation of the herbicidal formulations. The catalytic productions of the lactates is performed traditionally with mostly homogeneous catalyst. There are very few studies have been done with the heterogeneous catalyst. So homogeneous catalysts like anhydrous hydrogen chloride or sulfuric acid, phosphoric acid. So the other conventional acids are used as a homogeneous catalyst for the production of lactates. When we come for the hydrogenation of lactic acid and lactide, we produce propylene glycol. So you can see in this figure that lactic acid and lactate, it can be hydrogenated to produce 1,2-propanediol. So this propylene glycol, or also known as 1,2-propanediol, it also a commodity chemical with variety of use as a solvent for the production of unsaturated polyester resins or drugs or cosmetics or food industry. It has been used. So it is also used as a de-icing fluid or antifreeze property. It has production of this propylene glycol by the direct hydrogenation process of lactic acid or lactate can be a very good green alternative method to compared to the petroleum based process. Generally, direct hydrogenation of this carboxylic group are not practiced commercially, and instead the hydrogenation of the corresponding ester is performed to give better yield of the propylene glycol. Now this is due to the reactivity issue of the carbonyl group of the acids being lower than the esters, and also because acids react with the alcohol form and leading to formation of the ester. So these esters have high reactivity to produce the um, propylene glycol. So in any case, hydrogenation of the carboxylic acid or esters are often carried out under vigorous reactions conditions due to weak polarizability issues and intrinsic steric hindrance of the carbonyl group. Some ruthenium based catalysts have received recently lot of attention as a catalyst for this hydrogenation process of due to their intrinsic hydrogenation activity. Now, calcium lactate, the usual product from the fermentation, can be transformed directly to the propylene glycol by adding a stoichiometric quantity of sulfuric acid prior to hydrogenation. Okay, so dehydration process of the lactic acid, we mainly aim to produce the acrylic production for this process of dehydration. So you can see that mainly the main chemical is lactic acid, which is dehydrated to form acrylic acid. This acrylic acid, also known as commodity chemical of considerable value, and estimated annual production capacity is 4.2 metric tons. So this acrylic acid and its amide or esters derivative are the primary building blocks for manufacture of the acrylate polymers. Numerous applications have been performed or it is in practice for surface coating, textile, adhesive, paper treatment, leather, fiber, detergent, etc. Currently, 100% of the acrylic acid is produced out of fossil fuels, mostly via direct oxidation of the propane. Therefore, the production of the acrylic acid by dehydration of lactic acid, which will be very a- attractive target for the bio-based compounds. Salts and esters of lactic acid dehydrate more easily than the acid. Catalysts are involved like aluminophosphate treated with ammonia, calcium sulfate and zeolites are also used as a catalyst. Now, pyrolysis of the alpha acetoxy ethers of methyl lactate has been used as a route for converting the lactic acid to acrylates. So, this process it involves the treatment of ethyl lactate with acetic anhydride, giving it alpha acetoxy propionate. So this ester is then thermally decomposed to produce methyl acrylate and acetic acid. So we are this acetic acid also is a very important building block for commodity chemicals. Anaerobic formation of the acrylic acid is also performed by the dehydration of the lactic acid by some enzyme, that is lactyl CoA dehydrate. Sorry. So the dehydration of the lactic acid is performed by this lactyl CoA enzyme, which has been performed like by this Clostridium species microorganism. So they use the lactic acid as their energy source and giving the metabolic products um, such as propionic acid and acetic acid as their other byproduct. Kindly excuse for 5 minutes. Okay, so in this slide, we're going to discuss about the condensation uh, process, which is condensation of the lactic acid, which will give the 2,3 uh, which will give 2,3 pentanedione, and oxidation of the lactic acid to give pyruvic acid or pyruvates. So you can see in this figure that lactic acid condensation, it will form 2,3 pentanedione. In the vapor phase conditions, this lactic acid is condensed to produce 2,3 pentanedione using catalysts like sodium phosphate salts, which are supported on the silica alumina. This pyruvic acid and other auditor derivatives are the chemicals which obviously has large commercial value of this pyruvic acid and its derivatives, because it can be used as a precursor in synthesis of various drugs and agrochemicals. Pyruvic acid, which is prepared by the glucose fermentation process or enzyme catalyst reactions or chemical synthesis process. Established procedures for the production or synthesis of pyruvic acid are dehydrative carboxylation of tartaric acid in the presence of potassium hydrogen sulfate and the hydrolysis of the acetyl cyanide. So this alkyl lactates, which is generally methyl and ethyl esters, can be oxidized to corresponding pyruvates using different heterogeneous catalysts such as vanadium pentoxide, which is mixed with other catalyst as well, and some palladium platinum catalyst, lead modified palladium catalyst supported on carbon, phosphates and polyphosphates supported on silica. Those are used for the production of pyruvates. The direct oxidations of the lactic acid to pyruvic acid is much more difficult process. Most of the catalysts presented above, whatever be the examples it is written, they produce the oxidative C-C bond fission, converting the major part of the lactic acid to acetaldehyde and the CO2, rather than they don't produce the pyruvic acid. They produced lactic acid to acetaldehyde and carbon dioxide. In variety of living organism, lactate can be converted to pyruvate by lactate dehydrogenase. So which acts in the reverse reaction, but at the preparative scale, it is difficult to use this enzyme to obtain the pyruvate because stoichiometric amounts of expensive pyridine nucleotides has to be used. Those are expensive process. So you can see this lactate are taken like pyridine nucleotides to produce the pyruvate, but this process is very expensive as a industrial way. Industrial perspective. This lactate oxidase catalyzes the direct formations of the pyruvic acid from the lactic acid without requiring these pyridine nucleotides as a cofactor. It also gives hydrogen peroxide as a byproduct. So you can see that from this we are getting pyruvic acid as well as hydrogen peroxide as a byproduct. So this process is far economical than this process. Coming to the next platform chemical, that is the succinic acid. So succinic acid, anhydride or its ester form are the primary products from the um, malate or malic acid the hydrogenation process. While succinic acid is currently produced from butane through malic anhydride, it can be also produced by direct fermentation from the glucose. So most fermentation microorganisms are not tolerant to the acidic media, right? So fermentation process must be pH balanced or neutralized, producing salts of succinic acids. Conventional methodologies for separation and recovery of the succinic acid, they involve filtration and acidifications of the succinates to form succinic acid, whereas the salts are being precipitated. So we are separating out succinates from the succinic acid. So the succinic acid, which is chemically known as 1,4-butanoic acid. It is versatile compound able to undergo a variety of reactions to useful products. So the market potential for this product of succinic acid is almost very high per year, and including 1,4-butanediol, tetrahydrofuran, or butyrol acetone, or this kind of aliphatic esters are also as a product from the succinic acid. That these are some products that we can synthesize from the building block of the succinic acid. So there are direct hydrogenation process of the succinic acid, which succinic acid or succinic anhydride or succinates, which led to the formation of the product family such as 1,4-butanediol, that is known as BDO, tetrahydrofuran, THF, and butyro butyryl acetone, that is GBL. So this 1,4-butanediol is a compound which is a very good potential, having production of different kind of polymers such as polyesters, polyurethanes, polyethers. So majority of the BDO based polymers are polybutylene terephthalate, which is mainly used as a engineering plastic, fiber and film and adhesive as a purpose. Other video applications are formation of the THF, that is tetrahydrofuran, which is obtained by the homogeneous dehydration from the BDO. Okay, so THF is used as a solvent for polyvinyl chloride, that is PVC production, and also it is act as a monomer in the manufacture of the polytetramethyl glycol, which is also an intermediate of the spandex fiber formation or polyurethanes. So dehydrogenations of the BDO on the copper catalysis lead to formation of this GBL, which is another major solvent as an intermediate product for the agrochemical and pharmaceutical production. So the reaction of the GBL, when it happening with the ammonia or alkyl amines, they produce two pyrrolidone and N-alkyl pyrrolidones, which are used mostly as a solvent and starting material for the pharmaceutical. So the largest applications of these two pyrrolidone is like they produced uh, lot of pharmaceutical products, cosmetics, textile, paper, detergent, and beverages. So it has also been used like in methyl pyrrolidone. It is also used as a solvents in many of the industrial application. This figure you can see like our building block is succinic acid. So from there, by the dehydration, we are producing succinic anhydride. When it is acting with different alcohols, it is forming esters. From the esters, we are getting alkylidine succinates. When we come like succinic anhydride hydrogenation process, we are producing BDO. Uh, this is not BDO. This is butyryl acetone. When we form like hydrogenation of this butyryl acetone, we form BDO, and then from the BDO we do dehydration process, we form THF. So based upon this platform chemical as a succinic acid, we can see there are a lot of chemicals we can produce subsequently. Other chemicals from this succinic acid platform, that is, we are talking about 2-pyrrolidones, which are commercially produced by condensation of the GBL, which is produced by the hydrogenation of the malic or succinic anhydride with ammonia. It is reacting at a 520 Kelvin at very high pressure condition. However, another low cost and effective route to obtain the lactam in one step process, that is hydrogenation of the malic acid and or any malic acid derivatives or succinic acid or its derivative, using homogeneous or heterogeneous catalyst. By this hydrogenation we can produce these 2-pyrrolidones. So suppose some N-alkyl pyrrolidones can also be prepared from the succinic acid or its anhydride by reaction with alkylamines to form N-alkyl succinimides, which are then hydrogenated to form N-alkyl pyrrolidones using some catalysts like nickel oxide, aluminum oxide, silicon dioxide, graphite, etc. So you can see succinic anhydride, succinic acid, succinates, they can be reacted with amine or alkyl amines to form the 2-pyrrolidones in the ultimate product. Coming to the next acid platform, that is 3-hydroxypropanic acid. It is also known as a short form that we are talking about 3-HPA. It is a structural isomer of the lactic acid, which is also produced from the glucose fermentation. Like acetic acid, 3-HPA has also bifunctionality that allows multiple chemical transformation. So the acid group can be reduced to alcohol or can be converted to variety of esters, amide and derivatives. The alcohol function of the 3-HPA can be dehydrated and leading to unsaturated compounds. Moreover, the bifunctional nature of the 3-HPA also it allows the polymerization to polyester formation, oligomers and cyclization of the propio, propiolac, propiolactone and lactides. So in this figure you can see some converting routes for 3-HPA to industrially valuable product. We get from this building block we get dehydrated product as acrylic acid, and then it reacts with ammonia which form the acryl amide. When it reacts with methyl alcohol it forms methyl acrylate. When it dehydrates and it forms like malonic acid, it uh, hydrogenated, it forms 1,3-propanediol. So from this process, from acrylamide, we can also dehydrate and form acrylonitrile. So these many of chemicals you have must have heard about, like in the chemical technology applications in the course also. These are variously used in the polymer synthesis. So coming to the like other formation, that is 1,3-propanediol. is a starting material in the production of polyesters, so which are used together with the terephthalic acid to produce polyterimethylene terephthalate, uh, polytrimethylene terephthalate, which is in turn used for the manufacture of fibers on different resins. Copper and zinc oxide based catalysts, which are promoted with barium and zirconium uh, catalyst, which is also used for the gas phase hydrogenation of methyl 3 hydroxypropanate to form 1,3-propanediol using different alcohol, suppose methanol, as a solvent. This prevents self-lactonization and degradation of the reactant. So malic acid is also obtained by the oxidation process of 3-HPA, that is oxidation, it is producing malonic acid. So this poly 3 hydroxyproponic acid, which is also like polylactic acid, it is a bio-derived plastic with attractive lot of mechanical properties. It has like ductility, rigidity and exceptional tensile strength. So additionally, the polymer, it is enzymatically and hydrolytically degradable also, making it more environment friendly. So this poly 3 hydroxyproponic acid has been prepared by the condensation of the 3-HPA esters and by the ring opening polymerization of the beta propiolactone, which is catalyzed by different acid, base and salts. So coming to the other acid platforms that are represented in a like only figure format, that is itaconic acid and glutamic acid platforms. So here is the itaconic acid as a main block. We are also producing from that 3-methyl pyrrolidone, itaconic diamide, 2-methyl 1,4 butane diamine, 2-methyl 1,4 butanediol, and other chemicals like 3-methyl tetrahydrofuran. So this is also acting as a good chemical platform. So similarly, glutamic acid, when it acts as a platform, you can see that glucaric acid, pentanediol, glutaminol, polyglutamic acid, and then hydroxy and 4-amino 5-hydroxypentanoic acid, proline, prolinol, and pyroglutaminol. So these are some other chemicals that can be formed from these platform chemicals acid. So when we talk about the acetic acid, that we already discussed about some of the intermediate product as acetic acid production. So here it is a simple flowchart that you can see that cellulosic biomass is first step. It is produce some intermediates and then it is oxidized to acetic acid. In the product we are getting HMF or levulinic acid. From that we are getting acetic acid as an intermediate, and from there we have seen the acetic acid comes into a picture when we talked about lactic acid. So in the first step where the cellulosic biomass were primarily converted into intermediate product under in inert atmospheric conditions, so these intermediate are further oxidized to produce acetic acid. The formation of the intermediates in the first step, it varied when we add acid or base based upon that. So in the acidic two step process, so 5 hydroxymethyl fural was obtained by the dehydration of the monosaccharides, especially fructose, and then the levulinic acid was formed by the rehydration of the produced HMF, and then in the presence of the acid in the first step. And as for the selection of the mineral acid, HCl are reported to be more efficient in the reaction than other H2SO4 or phosphoric acid, probably due to the influence of the acid and anions. So, in the second step, the produced levulinic acid is further oxidized to produce the acetic acid out of that. So eventually the yield of the acetic acid becomes 23% to 26%, which is achieved from glucose and fructose using the HCl when we are using as a first step, and we are also using the hydrogen peroxide in the second step. So this is the overall process of the acetic acid, generally conventional process. So it can also be used as a different chemicals production from depending upon the acetic acid. So that's all for today's class. And regarding the last class doubt, like the question pattern and the numerical part, so I would like to suggest that kindly post your queries regarding the question pattern um, in the forum, that is in the NPTEL platform. So it will be easier to get direct clarification from the NPTEL team that we are mostly dealing with the theoretical part for this course. But if it is like um, numerical part, or the course instructor, that is professor, he will answer your question in that forum, or NPTEL team will answer your question. So better to post your question and queries in the forum regarding the NPTEL exam. So, in the next session, we will be discussing the last part of the course, that is the integrated bio refinery concept. Also, is economical analysis and life cycle analysis. So, is there any question from today's session that we can discuss?
Okay, ma'am. Thank you.
Okay, so thank you for joining. We will meet in the next session. That will be the last session. Okay, thank you.